I'm here again today with Peter Woodhead after a video we shot a few months ago back in April.
Yeah.
And I think I posted it in June, I think, didn't I? It's 12th
Yeah,
of June or something?
Yeah, 12th of June, yeah.
2014. So we've had about between 4 and 6 months of elapsed since then, really.
Mm.
And we posted the YouTube video and we got a few comments, and I think probably
most of them good, yeah.
Most of them good, I think.
Yeah.
Most of them. We did rile a few people, I think.
Yeah.
But that wasn't really the intention, obviously. But we just probably start off with a summary of what really part one was about. So, if we just do that in summary, then Peter, talk about, very quickly why you felt that this research was necessary.
Well, one of the main points was that I'd never seen a realistic explanation for how dinosaurs could roam the earth, being such enormous creatures that they were, especially the flying ones, pterodactyls the size of a light aircraft. How did they ever get off the ground in Earth's gravity as it's measured today? And the other thing was I came across these expanding Earth videos, as we pointed out, and I thought maybe there's a connection between the two. Now, the accepted wisdom of the expanding Earth people is that more and more actual mass is being attached to the Earth, and I thought, well, that doesn't work, because if you keep adding to the mass of the Earth, then its relationship with the Sun and the Moon would deteriorate, because the attraction would be getting much greater. And so I thought, well, the mass has to stay the same. So if the mass stays the same, then you've got to have some means of expanding the radius of the Earth to agree with the mid-ocean ridges and spreading. And so I thought about it, and I came across this article about the Atacama astronomy base, and we covered that.
So they found this star, it had a snow line around it, and they were basically saying that certain elements would freeze out, or a certain radius from the centre of the star, weren't they? And so,
as I've said, I thought that doesn't agree with the history books at all. No. So it just kind of came together that things are not what they were supposed to be, and that if we started off cold or relatively cold, we're going to come on to something else in a bit.
That's right. Yeah. That's really cold. Yeah.
So if it started off cold and it had a high proportion of water, now, as on the same day that you released the previous video,
this was one of the weird synchronicities, wasn't it?
This discovery of ringwoodite by seismologists studying. Well, I don't know what they were looking for, but what they found was this water-bearing rock.
Yeah. Exactly
where I said there would be a quantity of water, and in part one I speculated wildly as to what that proportion of water might be.
Yeah.
With the caveat that you didn't need a large amount of water to create the steam and gas powered volume underneath that layer.
And I think we'll just pause and just second that point and talk about, because we've been told, everyone says, oh, this hollow earth, it's all nonsense. And I mean, I've probably even used those very words myself in the past before, we got in touch and everything. But we're not really talking about hollow earth, really. We're talking about a gas-filled earth, aren't we? And I suppose we're probably going to say, when we talk, as we go through this, we're probably going to say hollow earth more than once accidentally, but really we mean gas-filled earth, don't we?
We do, yeah. And I treat the crust and the mantle as being the pressure vessel of containing this gas, and the effects that we see on the surface, either with volcanism and the spreading of the mid-ocean ridges, are symptoms of that pressure of gas and steam. And as we said in part 1, it can be seen on several moons.
We talked about that, yeah.
And only last week, NASA revealed that they thought there might be a lot of water slushing around inside
Mimas, which is one of the moons of Saturn.
So these revelations are coming out all the time.
Yeah, very synchronistically.
Yeah, suggesting that this is the time for people to wake up and see that things are not what we've been told.
And one of the things we mentioned, which we're going to come and try and cover in a bit more detail, because you've done a lot more work on this, is the issue of the explanation of gravity. Because we talked a minute ago about how the mass, the people like Neil Adams, who's done some excellent research and all the excellent videos, thinks the mass has increased. James Maxlow thinks the mass has increased.
Yeah.
But what you've done essentially shows that the mass hasn't increased, or at least not to any measurable extent.
No.
And what we're talking about, what you've put a lot of work into, is this essentially this working out where the mass is, really, or trying to sort of work out where the centre of mass is, or we've just come up with this term today from another forum called centre of mass force. So you've basically, I mean, we put forward this idea in the last video and on that posting that I did on my website, that the centre of gravity, what was it, 600 kilometres down? I can't remember the exact figure that you came up with.
Yeah, one of the things that came to light shortly after it had been posted was an assumption that I had made, was that this centre of force would be somewhere within the Earth's shell, if you like.
Yeah.
And that if you're on the inside of that shell, the gravity would be pointing towards the outside of the shell, and obviously on the surface it's pointing down.
Yeah.
So for the theory to work, I guesstimated, if you like, because I hadn't done the calculations then that I've done now, and I thought that centre of mass force would be within 300 or 500 kilometres of the surface, and that worked out fine with the rest of the theory in producing a gravity in the time of the dinosaurs of a quarter of what it is now.
Yes.
Now, as you've said, Neil Adams and James Maxlow believe that the mass of the Earth has been increasing, and that's why we're heavier now than we would have been 200 or 300 million years ago. But if you just do a direct back in time to when the radius was what it was then, which they agree with me, or I agree with them, that it's roughly 59 or 60%. It was then 59% of what it is now.
Yeah.
Then if you do the calculations for the weight of an animal, say, then it would be 59% of what it is now.
We're sort of proposing something different to this solid iron core. That's the thing. One of the things we think is wrong, and because the only reason for that was the magnetic field. That's the main reason why they needed that.
Yeah.
But we probably agree that there's some other reason for the Earth's magnetic field. We don't know exactly what that is. But then also, which we're going to come on to later, if we essentially getting rid of the molten iron core, that may mean, to give a little preview, that the mass of the Earth is a lot lower than is currently accepted, which we're going to talk about in a bit more detail. But I think before we go on to that, and we're going to do that in a couple of minutes, we did get some comments on part 1, didn't we?
Yeah.
And I know that Mr. Neil Adams, he wasn't totally happy with what we were proposing, but I think when we were speaking here, we didn't expect that he would be, which is fair enough. I mean, he's got his own research which he thinks is right, and that's fair enough. And then we had another chap called Michael Delaney, didn't we? Yeah. And he put quite a lot, because he had some. You told me about his comments, because
he made a lot of comments, and I'll hold my hand up and say I don't know what he was talking about a lot of the time.
Yeah.
But he made some remarks that made me think, which was about the failure rates of probes sent to the moon.
Yeah.
and that they were crashing, missing by miles, well, thousands of miles,
Yeah.
and things such as that. And so I started to think about what might be happening with the moon.
Yeah.
And I'm of the opinion that it formed at the same time as Earth, and that it was spinning, perhaps in the opposite direction to the Earth at the time. And that as time has gone on, the same process has gone on the moon, i.e. this heating through nuclear and whatever methods, and that it also has generated a gas-filled core, and there's evidence for expansion on the moon. But the difference with the moon is that the Earth's tidal effect on the moon has slowed its rotation down to a stop. So if you like, the distribution of mass in the moon could be very disproportionate, rather than having a shell such as Earth's,
yes,
which is pretty uniform and allows for circular orbits.
Yes.
On the moon, if the effects from the centre of mass force, or the centre of gravity, if you like, on the near side is much greater than the far side, then anybody wanting to put an orbiter in orbit around the moon would have to keep compensating to keep it in orbit. Otherwise, it's going to be going up, down, all over the place.
Right.
And that seems to be that's one of the things that Michael Delaney put me onto.
I see.
Was the failure rates in the early days.
Yes.
And so thanks to him for that, because
that's opened up another sort of avenue of doing calculations, hasn't it? And then I know we're not going to discuss this in detail, but I sent you that link to that article by Richard Hoagland, which was about Explorer 1, which I think was the first attempt at a US getting an orbit around. Was it around the Earth, or was it around the Earth?
No, it was an Earth. They were aiming for a particular circular orbit.
Yeah.
And what happened was they were sat waiting for the satellite to come back round the Earth after 90 minutes or so, and it didn't arrive. And so they thought, oh no, we're back to the drawing board. And then I think it was 8 minutes later it arrived.
Right.
And what they discovered was that they'd put it into a greatly exaggerated orbit, which was elliptical rather than circular. And as they used solid fuel rockets, they couldn't really explain why that would happen. But when you take into consideration some of the results I've got for the effect of gravity, you would expect it if you were charging this solid rocket to go into an orbit which you think was being governed by a force of gravity at that altitude, which is much greater than what I am going to say that it is.
Yeah.
Then you would have the effect of, once it reached its
projected height,
it's going to be overshoot.
Yeah.
And as was said about these probes crashing into the moon. So I think in the early days, they had, I don't know, did they come up with some kind of a fix or put a percentage of the power into the rockets? I don't know. But we know about secrecy, and as a friend of mine said, we would all know about it. No, we wouldn't.
Not necessarily, yeah.
Not necessarily, because NASA aren't going to share their secrets with the Russians, especially then.
Absolutely. I mean, we were discussing this, and basically what we're ending up saying is that if the centre of mass force is actually higher up in the Earth's body, nearer to the surface, then at the surface, we assume a certain mass of the Earth, and we know our mass of an object, so we base the calculations on those things, and we come out with a certain answer. And essentially what we're ending up saying is that the mass of the Earth may be much different to what's assumed. And when you're having a satellite being put in orbit or whatever, the force on that is different because the mass of the Earth is different, but also the centre of mass force, where the actual gravity appears to be coming from, if you will, is different as well. And those two figures together mean that, you know, they work at the surface, but when you go away from the surface, you end up with anomalies, which again we're going to talk about that in a few minutes with the Tibetan Plateau and so on. I think probably then that we're going to start to talk about those very calculations then, Peter. So
right. So as I said, every step of the way, I'm looking for confirmation in physical measurements.
Yeah.
And so one of the things that if you go online and do what would I weigh on top of Everest, you'll be directed to lots of sites that will say, well, here's the maths and how to do it, and your projected weight would, I think it would be 0.28%, because of the dropping off as gravity as you go. So
you'd actually weigh 0.28% less if you're on top of Everest,
Yeah, without going into specific numbers. It's just the percentage.
Yeah.
And that if you do my calculations with a centre mass force at 1,813, I mean, I believe when you get home you're going to check that, and
we'll check through that, and so we might end up with different figures in this.
With a different number. Yeah. But for now, we'll quote the numbers that I've got. So if you take that I'm suggesting, that 1,813 kilometres to the centre of mass force, and then add on the height of Everest, then you get something nearer to 1% of reduction in weight.
Right.
Which is nearly 4 times the difference between what you get by calculating using the accepted figures.
Yes.
So I thought, well, have they done gravity measurements at altitude?
Yeah.
And then they started falling out of the trees on me. And there are 2 good examples. The one is the gravity measurements of the Tibetan Plateau. Yeah. And at 5,000 and 6,000 metres, which is less than 2/3 of the height of Everest, you're getting readings of 0.6 and 0.5% reduction in the gravity measurement.
Right.
And the best one is in the Andes.
The Andes, in Peru.
Where you've got a mountain at 6,900 metres.
Yeah.
And it's got 0.7% reduction, and that's an actual measurement. Now, in all these cases, they're all described as gravity anomalies. Yeah. However, if the centre of mass force is really at 1,800 or so kilometres down, then they're perfectly predictable as being what you would expect them to be.
Because what you're essentially saying is that because the difference in the height that you're going up as a proportion of the distance down to where the centre of mass force or centre of gravity, if you want to call it that, is, becomes bigger, doesn't it? Because if you divide 9,000 by 180,000, whatever it works out to be, it's a much bigger number than if you divide it by 680,000. If we work it all out in the right figures. So that's essentially what we're saying, that when this centre of mass force is nearer to the surface, these gravitational differences, the measurable force, is greater, isn't it?
Yeah.
Because of the r squared factor in the
equation. So I was quite happy with that, because it backs up the theory in spades, and it very accurately becomes a predictor of what the gravity measurement would be at altitude. Then this also fits in with the original space missions and orbiters and what have you. They didn't get the expected orbit because they weren't expecting levels of gravity reduced by that amount. So I think that's an explanation for a lot of things going off
in the early days of
off in
space
the early
exploration.
days.
Yeah.
So,
Okay.
so I think they did come up with a fix for that, and they would have kept it to themselves. NASA would have kept it to themselves, and the Russians would have come up with a similar fix, and they would have kept it to themselves. But it's not widely available, and
No.
there's no reason why they would.
No, I mean, how many universities are launching rockets, and putting probes in orbit? There's not that many. There's probably only, 10 or something around the world, something like that.
You've got India and China launching things now.
But they've only done it in the last 10, 15, 20 years, haven't they?
Yeah, and then when they think, these calculations for G aren't right at altitude, who are they going to tell?
Exactly.
They're going to think, well,
and
we'll
we haven't really heard about their failures, have we, really? We just wouldn't hear about their failures,
No.
would we, really? It just wouldn't get into our news, even if it was reported. I mean, they might just not report it,
No.
That should give us pause that, we should maybe be prepared to re-examine some of these calculations, which I think is what, we're encouraging people to do.
Yeah, I mean, obviously now they've got it all figured out one way or another, because they've sent the Voyagers off into deep space and,
Absolutely. Yeah.
and landers on Mars and everything. So whatever, if it was a problem once, it's not anymore.
Yeah, they've worked around it, whatever issues there are.
On the same day that you released part 1, it was also released of a seismic survey that located all this water.
Yep.
Exactly where I said it would be. It's starting at 410 kilometres deep. So that was another confirmation for the theory, because if you've got, I was speculating wildly as to the amount of water that there might be down there.
Yes.
But it really didn't matter, as I made clear in part 1, because you only need a little bit of water to create that much steam.
Yes.
What did you say?
1,600 times.
1,600 times.
Pretty much, standard temperature pressure,
So even them suggesting that there was enough to refill the oceans 3 or 4 times over, that's more than enough to carry out the steam-powered expansion that we described.
Yeah.
And so that was very
eerie.
Yeah, it was coming out on the same day.
Because you sort of pointed out the differences in the depths on this figure. We'll show this figure on the screen.
The crust and the upper mantle are pretty much as acceptable to me as anybody else.
Yeah.
It was just below that I suspected this body of water. Now,
yes.
In number 1 we called it slush, for want of a better word, but these seismologists have said it's ringwoodite, which does occur on the surface, having been thrust up through volcanoes and such like.
Yeah.
And that the ringwoodite contains by volume 6 or 7% water. Yeah, so I was quite encouraged to discover that this seismic study had been carried out, and it discovered this transition zone, which I called the boiling zone, and that it contained a substance called ringwoodite, which contains about 6 or 7% water by volume. And as we've said before, the amount of water to create this steam-powered expansion, that's quite enough. Although I speculated at 30 to 70% or whatever in part 1, that figure doesn't really matter as long as you've got enough.
Yeah.
And by their calculations, I think they said there was water equivalent to 3 or 4 times the current volume of all the oceans. So that is more than enough.
Yeah.
So that is confirming the mechanism that I suggested in part 1.
Yeah.
Right. So the next bit of proof I was looking for is any kind of change in the value for the gravity being produced by a much reduced mass Earth.
Compared to the accepted mass,
Compared to the accepted mass.
Yeah.
Operating from a different depth within below the surface. Has got to affect anything in orbit.
So essentially what we're saying there is we've got a lower mass closer to the surface,
Yeah.
kind of thing, because the overall mass of the Earth is lower, but it's distributed in a way which is it's closer to the surface of the Earth. So
Yeah.
right, carry on from there.
Yeah, and it's another. I think the thread that goes through all these things, the dinosaurs, the orbits, the centre of mass force and everything,
Yes.
is all to do with the radius from which that force is operating squared. So I had a hunch that a lower mass Earth concentrated at a lower, a much less depth
Yeah.
might have the same effect on an orbiting object.
Object,
So I picked the ISS.
Yes, because we get quite a bit.
Yeah, you can
that.
go online and you can watch
Yeah.
it scootling about live.
Yeah. So you come out with that. We're proposing then a much lower mass of the Earth, and so without giving the exact figure, what proportion of that mass did you come out with compared to the accepted figure? What was the percentage? Roughly.
Roughly about 11%.
Right.
Because if you accept the density of the Earth to be the accepted density, which is including an iron core, so you get roughly 6 times 10 to the 24 kilos.
Okay.
Is the accepted value.
Okay.
I've calculated it from the expanding Earth theory to be 6.5 times 10 to the 23.
Right.
So you're looking at 11% or something of what is accepted.
Yeah.
But that 11% at that radius of 1813 plus 420 has exactly the same effect of keeping the ISS in orbit, pulling it down, which is in proportion to its velocity, which is keeping it up, if you like.
Yeah.
So both things work out well.
Yeah.
So although that doesn't prove the theory, it certainly means that it's not
ridiculous.
It's not ridiculous.
Yeah. Now I think what I'm going to show, and we'll try and do a spreadsheet of this, is you've done further calculations with these shells, haven't you?
Directly after you'd posted the part 1, wherein we had a graphic of a line within the Earth's shell that was say 300 or 500 kilometres deep, saying that the centre of mass force was somewhere within that shell.
Yeah.
And the first thing I realised when I saw the first part of the shell theory was that the calculations that work out that within, I'm going to say hollow, but because for the calculations it's hollow.
Hollow, yeah.
So for the calculations in a hollow sphere, there is no overall gravity acting in any direction. So basically, if you were popped into a hollow spherical object, you would just be drifting around it.
Yeah.
So I thought, well, I need something better than that, because obviously what we put into part 1, I could then see that was wrong.
Yeah.
And although I'd tried to do these calculations for the attraction between an object on the surface and the other parts of the shell, I hadn't done it, and I'd searched and didn't find anything. If you've got a problem and you want to know about something inside a sphere, you can find tons of it.
Of pages, yeah.
And if you want to talk about something that's on a stellar scale from an object, hundreds or thousands of miles away, then you can find that.
Yeah.
And you'll have no problems at all.
Yeah.
If you want to find the attraction between something stood on the surface and a shell, you struggle.
Yeah.
So to my own satisfaction, I produced a way of calculating, which is pretty much the same as the shell theorem.
Yeah.
Which I came across after I'd done this.
Yes.
The shell theory from a body outside the shell.
Right.
But if I'd have come across that, as I said earlier, I would have just thrown my arms up and said it's not possible, because that's all to do with differentiation and stuff that is beyond me.
You've done it in stages, didn't you? You've broken it down into steps and stages rather than trying to...
Yeah.
This is essentially done from first principles, isn't it?
Well, for my purposes, if you look at this shell, if you look at it in 2 dimensions as it's printed on this,
Yes.
The attraction between a body on the surface and the different segments of the shell have a vertical and a horizontal, if you like, or at 90 degrees.
Yeah.
Because that 90 degrees is cancelled out in all directions, you just get left with the vertical effect.
Component, yeah. And they're additive, aren't they?
Yeah.
Yeah.
So having divided this shell into 8 rings, I did the calculations, and that's how I arrived at a depth to the centre force mass, or centre mass force, of 1,813 kilometres. And perhaps just as importantly, if we go back then to the dinosaur argument, if in part 1 we said that the water was at the centre, originally ice and then water was a significant item at in the centre of the frozen planet, if you like. With the introduction of this ring woodite being perhaps 90% of that, and the density of the ring woodite being 3 point something kilos per litre.
Yes.
Then you have the fact that the centre of gravity, or centre of mass force, in the unexpanded or pre-expansion Earth would have been at a depth of 3,760 or so kilometres.
Right. Yes.
Yeah. So then, if the change from that centre of mass force has now moved to 1,800 and something, that is pretty much half the distance that the centre of mass force was pre-expansion. So what we get is the same thing that we had in part 1, a reduction of gravity by a quarter then compared with now.
Yeah, because that's, as you say, the radius of the centre of mass force is now half what it was, so we've got the force of gravity is reduced by half squared, which is a quarter.
Yeah,
which is about right for the calculations done with the dinosaur bones and that, isn't it?
Yeah.
So
but it's a lot more reliable figure now than it was in part 1, which was a lot of wild speculation.
Yeah. So this, again, it's all pointing towards, we might not have every detail right, but the overall thing is looking...
The principle is
pretty solid.
Yeah.
I mean, we probably mentioned this, we did talk about, for example, explaining the change in gravity by changing the gravitational constant, which, I mean, that's a whole other discussion, really, and how these... I know that Rupert, I think I mentioned in an email that Rupert Sheldrake had done a study a good few years about varying constants, such as the agreed speed of light, which has allegedly varied over the last 100 years. So we did talk about that a bit, but I think in explaining what you've explained there, that does, we can see that it's consistent.
Yeah.
But it will, just because it's consistent, it's not going to be popular, I don't think, because it's sort of smashing some accepted views and so on. And I think talking about the mass of the Earth, which you suggested there a few minutes ago that it was 11% roughly of the accepted mass. We'll go on to the gravitational binding energy in a minute, but if we go on and just say that, well, if the mass of the Earth is 11% less, what might that mean for the rest of the solar system? So if you want to talk about that.
Well, by inference rather than proof, if we establish a mass of the Earth of being 11% or so of what is generally accepted, then you're basically creating reducing the mass of the sun and the planets by the same margin to recreate the distances and orbits that we've got.
Yeah.
Also, you're looking at the moon being 11% of its accepted mass, and then when you do that, you realise that must have expanded by gas power.
Right, right. And then there are other people that have said this. I mean, there's another book that I think it was that book by Jan Lamprecht was called Hollow Planets, wasn't it? I mean, I've not read that book, but I think he actually called it.
Unfortunately, we're not going to be able to get to speak to him, are we?
No. But then, if we now go on to what Conrado sent to us, Conrado, our friend in Spain, who's looked into a lot of this stuff, he's got a very good mind, and he's sent me some very useful comments in the past. He said to me that we should talk about the gravitational binding energy, which is, there's a formula for this which is fairly straightforward, which I think is 3/5 gm squared over r. Yeah. So in other words, I'll try and explain that in that if we've got these swirling particles going around the sun and they're accreting into planets, then the kinetic energy which was in the motion of these particles, or lumps of rock, or whatever they were, however you characterise them, that they then coalesce, and that kinetic energy has got to go somewhere. So I think the standard accepted theory is that kinetic energy goes into the heating within the accretion, the secretion heating, and that I suppose is why they would argue that the Earth was a molten ball of lava or something. So this is one of the things that Conrado suggested we should try and account for, and following on from what we just said a few minutes ago, the gravitational binding energy, it's proportional to one over the radius, and we're working with when we go back to the pre-expansion Earth, it's about half the radius, isn't it? Yeah. From what we have now, so the radius obviously is smaller. But then, what Peter's just been describing there about the mass, we think the mass will also only be 10% of the accepted figure, which means that the mass squared would be 100 times smaller than the quantity that you come out with is 100 times smaller than what other people have calculated. And so you put these two factors together, in other words, the factor of 100 times smaller, but the radius is half, and you end up with 50 times less. So even if we did calculate this, gravitational binding energy, we would now say, based on what we've calculated with the calculations you've done, that it's going to be 50 times smaller than whatever figure. So in other words, it's going to be cooler. So the whole situation is going to be cooler than is currently accepted with the current figures. 50 times cooler. I mean, there may be some other factors to play into it, and then you've got factors of Newton's law of cooling and all of this, which I know a little bit about. But so this is very much we could do more work on that. It
puts a completely different slant on the 50 times cooler can on its own do away with this hot molten thing that has been cooling. And what we're saying is that it's been heated from within. So it's been getting hotter. Which is backed up by, if you accept that it's expanded, then for the first 4,000 million years, it was cold. And there was not enough heat to make it expand. Now, there are other people who say, it's been cooling and what have you. I'm just trying to build up enough evidence to show that this theory works.
And I mean, I think I tried to point out to Conrado that even when you take into account the gravitational binding energy, you've still got unknowns about how quickly it cools. We don't know the exact composition of all the materials, how quickly they were, the thermal transfer between those. We don't really know any of that stuff.
It would be an absolute minefield, wouldn't it?
It would, yeah. So, although what we're saying is some of it is, we are sort of guessing at parts of it, we're not doing anything different from what a lot of these other scientists are doing, because we haven't got these measurements going back hundreds of millions of years. We're inferring it just like they are inferring
We're putting it in its context. You're looking at an environment close to absolute zero. So ice, collisions is going to raise that temperature by what? Even if it raised it by 100 degrees, you're still
173 degrees
below freezing.
Yeah.
So you've still got the frost.
Absolutely. And then one of the other things we just wanted to mention briefly was the angular momentum calculations, because if you have a faster spinning globe, because I calculated on the spreadsheet that the rotation of the pre-expansion Earth was probably around about 8 hours. Compared to what.
I've even seen in scientific notes that it might have been down to 4 or 5 hours, but that didn't come out on the spreadsheet. But what is maintained is that there's an acceptance in the scientific community that the Earth's rotation is slowing down. And that is easily explained by expansion,
which is conservation of angular momentum right there, isn't it?
Yeah. And so you can predict that. You can go online and find this now, that the Earth's rotation is slowing down, and the measured amount by which it's slowing down.
So that also supports the.
So that supports the theory.
The expanding Earth.
In fact, you could, if you were just given the day length figures of a shell, for example, you could calculate
the radius.
The radius. By the difference in angular momentum. So the people who want to deny this theory have got a few different things to overcome before they can.
They just say it's an anomaly and they don't explain it, though. That's the way.
Anomaly is a word that I keep coming across.
Absolutely, And then, for example, we'd also seen this quite recently of examples of recent volcanism. I'm not sure which correct. I think it's volcanism on the moon. And we've already argued. I'll put this picture on the screen from the NASA story and the one that you found in the last week or two. That this appears then to support the idea that the moon is venting as well, like the Earth is, because it's slowly expanding. And of course, Neil Adams says that as well. He said the moon's expanding, and he's done videos for the moon, hasn't he?
I think the gravity orbiters that are measuring the effect of gravity on the moon have really revealed something that can't be seen on the surface. So these, what I would call rift valleys, have been filled in by the moon's magma flows, and so from the Earth they're invisible, but using the gravity scans that they're doing now, they're becoming quite visible as valleys.
So again, that ties in with it. And then the other thing we just mentioned very briefly, I think, just to sort of give a nod to the thought, is the abiotic oil. And if we consider how the gas is venting from the Earth's centre through the mantle, through the other materials and the water, that's going to create all kinds of sort of mixes of organic chemicals and hydrocarbons, and when you've got heat and pressure, you're going to get all kinds of things going on. So this could well account for abiotic oil as well, couldn't it? A high proportion of what's going on with that.
The theory of abiotic oil has been around for 100 years or more. And we keep being told that we've got to cut back on use of our fossil fuels. Well, oil is found at depths hundreds of kilometres. Well, not hundreds of kilometres, tens of kilometres below the point where any life has ever existed on our planet. So it's not a fossil, is it?
No.
It's a conversion from methane or other gases under pressure, under heat, into oil. And they're now finding that oil fields, which have been declared empty, have filled up again from deeper reserves of oil, which then filter up through the crust. And one of the explanations for the disaster in the Gulf was that they were going for one of these deeper reservoirs of oil. But the fact of the matter is that it's not fossil fuel, and it's not finite. It's being reproduced as we speak.
Yeah, I tend to agree.
Not that I'm a big fan of using.
I mean, we do.
I nearly said fossil fuels then, but
yeah, we don't need them.
We don't need them. There's so many other means of generating the world's power.
Yeah.
But they're all behind bars.
Yeah, a lot of the people are. Okay, well, I think then hopefully people will look at this again, treat it the same as part one. You know, we freely admit we're not geologists, we're not earth scientists, etc., etc. But you know, we've got the evidence, we've got the calculations, and if people want to contribute, make corrections, suggest, you know, enhancements and whatever, or as Conrado did, this pointing out the you know, the accretion calculations and so forth, fantastic. But you know, at the end of the day, it's take it or leave it. You know, we don't gain anything from this particularly, except our own satisfaction of, you know, uncovering some of this and trying to make people think about it. But again, Peter, I'd like to thank you for all the work you've done on the calculations and for hosting me again here today. And
thank you for all that you've done, because you put it into an agreeable format.
Yeah, well, we'll try and do that again for part two, and hopefully that'll correct some of the mistakes, and maybe the mistakes in this, but we live and learn by those mistakes, and hopefully are better for that. So, so again, thank you very much. We may even do a part three. Who knows?
Who knows?
Great.
Thanks for that.